Hi and welcome to a technical presentation. This video highlights some of the geological insights that we have gained from a recent academic visit. Before we begin, let me introduce our group members. We are Group 3 from KNS1102 Engineering Geology. The team consists of Ms. Alia, Ms. Nur Syazatul Farahin, Ms. Shamin Natasha, Ms. Nur Fatia, and myself, Muhammad Rahmat. Now let's get into the main content of this presentation.
For our report, we visited the Department of Geoscience and Minerals or JMG in Kuching to learn more about the difference of rocks, minerals, and fossils found in Malaysia. During the visit, we explored examples of igneous, sedimentary, and metamorphic rocks, along with various minerals and fossils. This experience was especially valuable for us as civil engineering students because understanding these natural materials helps in selecting the right ones for construction projects. Each type of rock or mineral has unique properties that can affect the strength, durability, and safety of a structure. The visit also showed us how geology plays an important role in developing sustainable and safe infrastructure in the real world.
Greetings, my name is Alia Anamigai with number matrix of 102412. Today, I would like to present about igneous rock and sedimentary rock. Firstly, igneous rock form from the cooling and solidifications of magma or lava. It can form by slowly cooling beneath the surface or more rapidly at the surface. It was divided into two types, which is plutonic and volcanic. First, plutonic igneous rock are formed from the cooling and solidifications of magma beneath the Earth's surface. The magma usually will take a long time to completely solidify as it undergoes slow cooling. This will result in coarse grained rock. An example of plutonic igneous rock is adamalite. A plutonic igneous rock usually found in massive size because of the underground formation, which making them enough time to grow larger. Next is volcanic igneous rock. It was formed when magma arises from the below of the earth and cool down on the its surface. During this process, the magma will cool down rapidly, resulting in formations of aphanitic texture, or what we call glassy look rock. An example of volcanic igneous rock is basalt. Basalt is a fine-grained texture due to the rapidly cooling magma or lava, resulting in no crystallizations. Next is sedimentary rock, formed by the compaction and cementing together of sediments. This rock can be formed from erosions and weathering of other rocks. Sedimentary rock can be divided into two types, which is clastic and non-clastic. Clastic sedimentary rock are formed by compacted and cemented small-sized fragments from pre-existing rocks. An example of clastic sedimentary rock is sandstone. Sandstone consists of sand-sized grains of a variety of minerals such as clay, mineral, feldspar, and lithic in uniform size. Next is non-clastic sedimentary rock. It was formed Next is non-clastic sedimentary rock. It was formed when silicon dioxide microcrystal grow in soft sediment like limestone or chalk. These microcrystal turn into irregular nodules or concretions, creating continuous notch layer. An example of non-clastic sedimentary rock is chert. It came from biological sources such as diatom, radiolarians. It is found in carbonate rocks like greensand, limestone, chalk, and dolostone formation as exchange mineral.
Now we will talk about metamorphic rock. Metamorphic rock produce when sedimentary or igneous rock are transformed by heat and pressure. These extreme conditions are only present deep inside the earth. So, metamorphic rock are classified into two main types based on how they form: regional and contact metamorphism. Regional metamorphism is one type of metamorphism in geology. It is the widespread transformations of rock under high temperature and pressure conditions. Regional metamorphism occurs during the formation of mountain ranges. As tectonic plates collide and converge. Intense pressure deform and alter sedimentary and igneous rock already buried in the earth. Floats or curves in the rock indicate the direction of intense pressure. An example of a rock formed by regional metamorphism is schist or gneiss, which shows clear layering or foliation due to the directional pressure. Now let's move on to contact metamorphism. Contact metamorphism is one of the main types of metamorphism. It is the transformation rock undergo. They come into contact with a very high heat source. Contact metamorphism occurs when a rock is exposed to hot magma inside the earth. The intense heat of the magma alters the rock, often causing its mineral to recrystallize. The area of the rock affected by contact metamorphism is appropriately known as the back zone. A common example is hornfels, which form when shale or other rock are baked by the heat. In summary, regional metamorphism affects a large area due to the pressure and heat from tectonic activity, while contact metamorphism occurs in a smaller zone, driven mainly by heat from magma.
Hi, my name is Nur Fatia. Today, I'll be sharing about three main types of minerals, which are metallic, non-metallic, and precious. Metallic minerals have a shiny metal-like appearance and can conduct electricity. A good example is the quartz calcite vein, which forms from intergrown crystals in fractures. Quartz is harder and doesn't react with acid, while calcite is softer and has a perfect cleavage and reacts with acid. Non-metallic minerals, on the other hand, don't look like metal and can't conduct electricity. They are usually dull or glassy. One example is galena, which actually has a metallic luster and forms cubic crystals. It is lead gray, soft, very dense, and is the main source of lead. It is commonly found with sulfurite and quartz. Lastly, we have precious minerals, which are rare, valuable, and often used in jewelry for their beauty and durability. Crystal quartz is a great example. It is tough, colorless to white, and has no cleavage and a hardness of 7. It has a glassy appearance, doesn't react with acid, and is also used in electronics. These differences help us understand how minerals are classified and what they are commonly used for.
Now we have fossils. There are three types of fossils, which is macrofossil, microfossil, and also trace fossil. So macrofossil is a large fossilized remains or imprints of plants and animals that can be seen and manipulated by the naked eye. As you can see here, there is a macrofossil of dinosaur bone, and due to its large size, we don't need an equipment to see or study them. Next, we have microfossil, which is a microscopic fossils, typically less than 1 to 2 millimeters in size, which require a microscope for study. So as you can see here, there is a microfossil of Foraminifera, which is a type of amoeba microorganism. Due to its a very small size, we need an equipment such as scanning electron microscope (SEM) to study them. Lastly, we have trace fossil, which is a geological records of biological activity, specifically the preserved evidence of an organism's behavior rather than its physical remains. As you can see here, there is a trace fossil of a footprint of dinosaur, which is from million to billion years ago, that we can still see it until now. Uses of fossils. So macrofossils, as we know, they are the visible remains of organisms like bones, leaves, or shells. There are a few uses of macrofossils, including understanding evolution and extinction. In other words, macrofossils help to track changes in life forms through time. Next, macrofossils help to reconstructing ancient ecosystems. These show the types of plants, animals, and their interactions. Lastly, macrofossils help to interpret climate change. according to the fossil leaves or shells that can indicate the past temperature and environment. Next is microfossils, which are microscopic remains like pollen, plankton, or tiny shells, basically a very small organisms. So some of the uses of microfossils is including biostratigraphy, dating rocks, which is ideal for correlating layers over large areas due to the rapid evolution. Other than that, microfossils also help in paleoclimatology, which is to study the species diversity and chemical composition that shows climate changes. And lastly, microfossils also help in forensic and archaeology studies, which is to study microfossils in soil or artifacts help in the location or dating. Trace fossils record activity or behavior such as footprints, burrows, or feces. Some of the uses of trace fossils is in behavioral studies, which can show the movement, feeding, nesting, or social behavior of an organism. Next, trace fossils also help to identify the presence of life even when no body fossils are found. It also helps in estimating the size and speed of organisms based on footprint length and spacing that can suggest how big or fast the creature was.
Similar rocks and minerals. Firstly, let's look at similar rocks that can be easily confused based on appearance. One example is basalt versus gabbro. Both are dark-colored igneous rocks. The key difference lies in their texture and how they form. Basalt is fine-grained and forms at the surface from a lava that cools quickly, which makes it an extrusive rock. Gabbro, on the other hand, is coarse-grained and forms deep underground from slowly cooled magma, so it is an intrusive rock. Even though they look quite similar, the grain size and cooling environment set them apart. Another pair of confusing rocks is slate and schist, which are both foliated metamorphic rocks. Slate has fine grains and a smooth surface, often used in roofing or tiles. Schist, in contrast, has a more visible mineral alignment with sparkling surfaces due to the presence of mica and other minerals. The difference is largely in the grade of metamorphism. Schist forms at a higher temperature and pressure than slate, which results in a coarser texture. Moving on to the minerals with similar internal structures, first up we have quartz and calcite. At first glance they can appear similar, both can be white or transparent with a glassy luster. However, quartz is much harder. It can scratch glass while calcite cannot. Quartz also has no cleavage, whereas calcite has perfect cleavage in 3 directions and reacts with acid, which is a key test in mineral identification. Another comparison is agate versus jasper pebble. Both are forms of microcrystalline quartz with the same hexagonal internal structure, but they differ in appearance. Agate is typically banded and translucent, while jasper is opaque and often has a uniform or speckled color due to impurities. These visual differences help geologists distinguish between the two, even though they internally are quite similar. Now let's explore some of the commercial uses of minerals we have observed. Galena serves as a main source of lead, pyrite provides sulfur, and sphalerite is mined for zinc. We also observed an arsenic ore, which is commonly extracted for industrial uses such as wood preservation, semiconductors, and pesticides. These minerals have significant economic importance across different industries. In terms of engineering applications, quartz crystal is used widely due to its stability and hardness, especially in construction as quartz sand and also in glass and electronic manufacturing. And serpentinite, a metamorphic rock, is used as a dimension stone, and in some cases a filler material in construction. These uses highlight how mineral properties directly influence engineering decisions. Some minerals are also valued for their aesthetic and symbolic appeal. Agate, with its beautiful banding, is used in jewelry, ornamental items, and interior decorations. Quartz crystal, especially when clear, is a popular material for carvings, decorative items, and even spiritual purposes. These minerals not only serve functional roles but also contribute to art and culture. In conclusion, our visit to the Department of Geoscience and Minerals (JMG) has given us valuable insights into the wide range of rocks and minerals that is found in Malaysia. We learned how formation processes, textures, and internal structures influence the appearance, classifications, and practical applications of these materials. This knowledge is especially important in civil engineering, where understanding the characteristics of geological materials is essential for selecting safe, durable, and sustainable materials in construction. Overall, this experience has helped us better understand the relationship between geology and engineering practice, and we hope to apply this knowledge in future projects.